Today we're going to do revision about groups, and you already know about groups already, so this is all going to be very easy. Remember that a group is a set equipped with a binary operation, only one binary operation. We've been doing rings that have two binary operations, so in a way it's all got easier now because we've only got one binary operation again. So here's the definition of a group. A group G is a set equipped with a binary operation which we'll write usually as a dot, or we'll leave it out together. And the point of this binary operation is it says if you've got two elements of your group, you can put them together and they'll miraculously transform into a different element of the group, or an element of the group anyway. And this has to satisfy some axioms. The usual axioms: associativity, there has to be an identity, and everything has to have an inverse. So we've got associativity, everything has to have, there has to be an identity element, and everything has to have an inverse. So you should stop now and see if you can write down those axioms for yourself. Now I'll do them for you. Associativity says for all A and B in the group, A, B, C has to equal A, B, C, and remember it's called associativity because we've associated these two elements together and then we've associated those two elements together. The identity, that says that there exists an element E in the group such that for all elements G in the group, G times E equals G and is the same as E times G. And the inverse says that for every element of the group, there's another one that causes it to collapse back to the identity again. So for all G in the group, there exists G inverse in the group such that G times G inverse is the identity, and that's the same as G inverse times G. And we have to write these both ways round because this operation isn't necessarily commutative. So GH isn't necessarily the same as HG, and if it is, it's called abelian. Right, so what about the order of a group? The order of G, which we write as G inside modular signs, and don't get this confused with the order of an element, remember, the order of a group G is the number of elements in the group. What about the order of an element? The order of an element G in G is the smallest k such that G to the power of k is the identity. And remember, you have to say it's the smallest one. It won't do if you just find any old k such that G to the k is the identity. You have to check G squared, G cubed, G to the 4, G to the 5, G to the 6, and so on, and make sure that no smaller number managed to get you back to the identity. So is the smallest k natural number k such that G to the k is the identity. So we have some of our favourite examples. We have Sn, the group of permutations of n elements. How many elements are there in Sn? Well, if you're going to permute n elements, you've got to decide what order they're going to go in. And how many choices have you got for the first element? Well, you've got n choices for the first element, n minus 1 choices for the second element, n minus 2 choices for the third element, and so on, until you've only got one element left. You multiply all those choices together, and you've got how many elements? How many permutations? Of course, it's n factorial. This is also called the nth symmetric group. And remember that there are two kinds of notation for this. There's two-row notation, so the example that we've got here is 1, 2, 3, 4, 5, 6, goes to 2, 4, 5, 1, 3, 6. And we can rewrite this in disjoint cycle notation. So this permutation tells us that it writes it out explicitly where everybody goes. 1 goes to 2, 2 goes to 4, 3 goes to 5, 4 goes to 1, 5 goes to 3, and 6 goes to 6, stays still. Whereas in disjoint cycle notation, we write the actual journeys that each element goes on as it kind of moves around the permutation. So let's try that. Start with 1. Where does 1 go first? 1 goes to 2. And then where does 2 go? 2 goes to 4. And then where does 4 go? 4 goes to 1. Oh, it goes back to 1 again. So this is a cycle, and we close it off. Because remember, when you put the brackets around it, that means you go round and round this loop. So what's the first element we haven't used yet? It's 3. Where does 3 go? 3 goes to 5. Where does 5 go? Oh, it goes back to 3 again. That's another cycle. And finally, there's 6. 6 stays still. So I'm not going to write that down. I think we should omit 1 cycles. So this is that element in disjoint cycle notation. So that's the disjoint cycle notation. And note that what we've got here is a 3 cycle. A 3 cycle followed by a 2 cycle. So the cycle type is 3, 2, which is to say it's a 3 cycle followed by a 2 cycle when we write it in disjoint cycle notation. So all I've done is I've abbreviated 3 cycle, 2 cycle to 3, 2, and that's the cycle type of that element. Now remember, every element, every permutation can be written as a product of transpositions. A transposition is a 2 cycle. It just transposes 2 elements. So how can we write this one, 1, 2, 4, 3, 5, as a product of transpositions? See if you can write that down now. And remember, the key to this is to remember how you do a K cycle. If we do 1, 2, 3, 4, 5, we can write this as a product of transpositions. How? Very easy. You go 1, 2, 2, 3, 3, 4, 4, 5. Should we just check that that actually does the thing we want it to? Remember that when we multiply permutations together, we feed in from the right-hand side. So let's see what happens if we feed the numbers in from this side. If we feed in 1, boring, 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 ping, 1 goes to 2. If we feed in 2, boring, 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 ping, 2 goes to 3, boring. So 2 does in fact go to 3. 3 goes to 4, 4 goes to 5, and 5 gets to have the most fun because 5 goes ping, goes into 4, then it turns into 3, then it turns into 2, and then it turns into 1. So it really does, 5 really does get to go back there. People sometimes accidentally add on an extra 1, 5 at the end. That's bad, don't do that. So we don't need an extra 1, 5 at the end. So now we know how to do any K cycle, right? Because it didn't matter if this was 5, we could just keep going. And so this one, first we do the 3 cycle, which is 1, 2, 2, 4, and then we do the 2 cycle at the end, which just is what it is. So we've now expressed that as a product of transpositions. They're not necessarily disjoint anymore because, of course, every time we had a cycle longer than 2, we couldn't be disjoint. And the other thing is, it's not unique. There are lots of different ways of doing it. You might have seen other ways of doing K cycles. I happen to think this is the easiest way. But here's something really stupid you could do. You could have done 1, 2, 2, 3, 3, 4, 4, 5. Then we could have done 1, 2, 1, 2. And you know what that is? That is a moment of futility. We've put in a 1, 2 and immediately taken it out again. which is a bit pointless, except it's not pointless because it's demonstrated a very profound point, which is that this expression is not unique. So the expression is not unique. But something that is true about it is that all expressions of the same element will have the same parity, which is to say that if you got an even number of transpositions by one way of doing it and you did it by a different way, you'd both get an even number of transpositions no matter how you did it. Or if you got an odd number and you got an odd number, then you'd both get an odd, let me start again. If you got an odd number, you would have to get an odd number, definitely. So every different way of doing it gives you the same parity of number of transpositions. And if you get an even number, then it's an even permutation. And if you get an odd number, it's called an odd permutation. So then the question is, do the even permutations form a subgroup? The even permutations, yes, they do form a subgroup. Yes. How do you multiply permutations together? Well, you stick them side by side. If you stick together an even number of permutations and then another even number of permutations, how many permutations have you got altogether? Well, it's definitely an even number, right? So that's definitely even. What about the odd ones? If you stick together an odd number of permutations, transpositions, and an odd number of transpositions, how many have you got altogether? Oh dear, now you've got an even number of transpositions. So that's not going to be a subgroup. The odd permutations do not form a subgroup because odd perm times odd perm equals even perm. Don't get confused about the fact that odd times odd is odd when you're talking about numbers, because what we're doing is counting the number of transpositions. Because if you have k transpositions here and you have j transpositions here, how many transpositions do you have in the product? K plus j transpositions. And so if this is odd and this is odd, then you get odd plus odd transpositions, which is even. Right. How many? AN is the even permutations. The even permutations, that's AN. The alternating group. And how many elements are there? So that's the even permutations. How many elements are there in AN? Well, there's exactly half even permutations and half odd permutations. So the answer is n factorial over 2. Right, some questions about Sn. Is Sn abelian? Which is to say, do all the elements commute with each other? Well, some of them do, and some of them don't, is the answer. So Sn is not abelian for n greater than 2. If n equals 2, S2 isn't very interesting, right? S2 has only 2 elements, whereas S3 and above is much more interesting. So I've given you an example right here. For example, 1, 2, 2, 3 is 1, 2, 3, and 1, 2, switch them over, 2, 3, 1, 2 is not 1, 2, 3. Let's see what it is. 1 goes to 2, which goes to 3, 3 goes to 2, and 2 goes back to 1 again. So these are not, these do not commute. So the group is not abelian. Right. Definition 4.1.5, a subgroup of G is a subset such that it's also a group and it's got to have the same operation. That's the really crucial point. remember? So don't forget that crucial point. It's like with rings, you've got to inherit the same operation to be a subgroup. Cyclic groups, we've got the cyclic group of order n. That's not too difficult. What about symmetric groups? Dn is the group of symmetries of the regular n-sided polygon. 1 and 2 are slightly peculiar, so we'll leave them for now. But what about Dn? So Dn is the symmetries of the regular n-sided polygon, which is also known as an n-gon, which looks pretty stupid and sounds pretty stupid, but it's easier to say than n-sided polygon all the time. How many elements are there in Dn? Well, that's 2n, of course, because if you've got an n-sided polygon, then how many symmetries have you got? You've got n reflections, one through each side or pair of vertices, depending on whether you're odd or even, and then you've got n rotations as well. And so that's the answer to the next part. It's got n rotations and n reflections. The group is generated by one rotation and one reflection, which means that if I fix your arm so that you're only able to go for one rotation and you're only able to go for one reflection, you'd still be able to generate every element of the group just by repeatedly going and as many times as you wanted. That's what generating means. The rotations form a subgroup which is isomorphic to the cyclic group of order n. Right, what's the next example? The next example is O2, the group of symmetries of the circle. How many elements are there in O2? Well, O2 is infinite because, as the little boys said to me at school, there's lines of symmetry like that, and there's more like that, and then there's more like that, and there's hundreds of them! There's thousands of them! You could keep drawing them all day and you'd never finish! Or you can do that, and you've drawn them all. Right. So it's these famous rot and ref things. There's rotations by every angle alpha, so of course there's an infinite number of them, and there's also reflections in any angle. There's an infinite number of those as well. You can now generate this group by one reflection and all the rotations. If I fix your arm so you can only go you'll never be able to get all the rotations of the circle because there are really, really tiny ones that you'll never hit. We've got some more examples. SO2 is the rotation group of the circle, and it's a subgroup of all the symmetries of the circle. Here's an interesting one. D1 is isomorphic to C2, which is isomorphic to S2. And we know that even without thinking, because remember I told you before, there is only one possible group of order 2. So all groups of order 2 are isomorphic. I suppose we haven't exactly said what isomorphic means, but you've done that before, so I'm assuming you know what it means. It means they're basically all the same, or if you draw out their Cayley table, you will definitely get a Battenberg cake for the Cayley table. And D1 has order 2, although I haven't really told you what it is, but it must have order 2 because it's got to have order 2 times 1. C2 has order 2 and S2 has order 2, so they must all be isomorphic. But also, actually, we can show that all groups of order 3 are isomorphic as well. And so, also all groups of order P prime are isomorphic because they're all isomorphic to the cyclic group of order P. That's something we're going to show later. But this next one is a bit exciting because D3 How many elements has D3 got? It's got 6 elements. And S3 also has 6 elements, and they turn out to be isomorphic as well. But not all groups of order 6 are isomorphic. So for example, these are not isomorphic to the cyclic group of order 6. So we'll see about that later, how we can prove that D3 is isomorphic to S3. And in fact, that's the smallest possible non-abelian group. How many elements are there in D3? 6. So all groups of order 2, 3, 4 and 5 have to be abelian. They're forced to be abelian. There's not enough room for anybody to be non-abelian until we get to 6. Right. And the last example, 4.1.8, we have here is groups of matrices. Do the n by n real matrices form a group under multiplication? The n by n real matrices under multiplication do not form a group. Because they might not have inverses. Right? Not every matrix has an inverse. When does it have an inverse? Only if the determinant is non-zero. So we can restrict to those ones, and that's called the general linear group, GL, of n by n matrices with numbers, coefficients in the real numbers. This is the group of invertible real matrices. The group of invertible real n by n matrices under multiplication. And we can do that in any field, right? We know that we can make a ring of matrices in any ring, but we can do a group of invertible real matrices and put any field F in there, because we've got to be able to invert the elements inside there as well. This is called the general linear group. And then the second example, you can restrict even further to those that only have determinant 1, and this is the special linear group, which is a subgroup of GLNF of determinant 1 matrices. Could we restrict to matrices of determinant 2? The answer is no, we couldn't do that, because if we multiplied them together, they wouldn't still have determinant 2. So we cannot restrict to matrices of determinant 2, since this won't be closed under multiplication. Right, remember that the determinant of AB is the determinant of A times the determinant of B. So if we start with matrices of determinant 2, when we multiply them together, we'll get matrices of determinant 4. That's no good. Whereas if we restrict to those of determinant 1, when we multiply them together, they'll still have determinant 1, so we'll still be in the group that we started with. So that one is a subgroup. And now, in the next video, we'll go on to some theory of groups.